Okay, let's talk about recommender systems. You know, the invisible engines that power everything from the movies you watch to the stuff you buy online. We all know they're everywhere, but let's be honest, they're often not very good. Today, we're diving into a really powerful new idea that flips the whole problem on its head. What if a great recommendation isn't about prediction, but about cleaning up a messy puzzle?
Seriously, why is this still so hard? We've all been there, right? You get a recommendation for something you literally just bought, or for something that is so far off you wonder if the algorithm knows you at all. It feels like these systems just don't get us. So what's going on under the hood? Well, to really appreciate the new solution, we first have to understand why the old methods just aren't cutting it anymore.
All right, so to see why this new approach, DiffRec, is such a big deal, we got to look at the last generation of what were considered top-tier models. We need to see exactly where they stumbled. The two big players on the field were variational autoencoders, which you'll see called VAEs, and generative adversarial networks, or GANs.
Now, these two models, as powerful as they were, each had a kind of fatal flaw. VAEs, on the one hand, try to take all your complex, unique, kind of weird tastes and squeeze them into a nice, simple statistical box, like a perfect bell curve. The problem is, this creates an information bottleneck. It smooths out all the interesting edges and leaves you with blurry, generic recommendations. Then you have GANs. They're way more flexible, but they are notoriously unstable to train. They often fall into this trap called mode collapse, which is a fancy way of saying the model gets lazy and just learns to recommend the same handful of super popular items to everybody. It's a safe bet for the model, but it's not personal at all.
So, how do we break out of this rut? Well, the answer, and this is the cool part, comes from a totally different field: computer vision. You've definitely seen those mind-blowing AI-generated images, right? The tech behind a lot of them is called a diffusion model, and it is a completely different way of thinking about how to create something new.
So what is a diffusion model? At its absolute core, it's a master of restoration. See, it doesn't try to create something from a totally blank slate. Instead, it learns how to take a completely corrupted, noisy mess and meticulously, step by step, clean it up until it becomes a perfect, coherent piece of data.
Let's stick with the image analogy, because it makes this super clear. Imagine the process starts with a perfectly clean, crisp image. Then, in what's called the forward process, the system deliberately adds a tiny bit of mathematical noise. Think of it like TV static. It does this over and over, hundreds or even thousands of times, until the original image is completely gone. It's just a screen of pure static.
Now, here comes the magic. The AI's entire job is to learn how to perfectly reverse that process. It's trained to look at any of those noisy steps and just predict what the slightly cleaner version looked like one step before. And by doing this over and over again, it can start with pure noise and literally denoise its way all the way back to that original pristine image. This is the reverse process, and it's where the generative power comes from.
Okay, that is a really cool trick for making images, for sure. But what on earth does it have to do with recommending you a new book or a movie? Well, this is where the researchers had a truly brilliant insight. Your interaction history, that list of things you've clicked on, watched, or bought, can be treated just like that image.
And believe it or not, the process is almost identical to what we just saw with images. First, in the forward process, DiffRec takes a user's known history, all their clicks, and systematically corrupts it with mathematical noise. Then, in the reverse process, it trains a neural network to take that noisy, messy history and painstakingly denoise it. The final perfectly clean version? That represents the model's best guess of your true, complete preferences, including all the stuff you'd absolutely love but haven't even discovered yet. This is a huge paradigm shift. Think about it. Old models saw the noise in your history, accidental clicks, things you tried and hated, as a problem to be ignored or filtered out. DiffRec flips that whole idea on its head. It makes noise the central feature. By explicitly training a model to denoise, it becomes incredibly good at telling the difference between the real signal of your taste and just the random static of your behavior.
But they had to make one crucial change to make this work for recommendations. With an image, you can corrupt it all the way at a pure static. But if you did that with a user's history, you'd completely erase any hint of their personal taste. So DiffRec does something really smart. It stops the noising process early. It ensures that even the most corrupted version of your history still has a faint, recoverable signal of you, the original user. This is the key to keeping the recommendations personal.
So, this all sounds really elegant, really clever in theory, but the billion-dollar question for any new model is always the same. Does it actually work any better? Well,
Let's take a look at the evidence, because the results are pretty darn clear.
Check out this table. These are the results on a standard dataset for recommending books on Amazon. Multi-VA, that's our old champion, the VAE-based model. LightGCN is a really powerful, state-of-the-art model that uses graph neural networks. And then you have DiffRec. As you can see, DiffRec doesn't just squeak by, it beats them both by a really significant margin. What's so amazing here is that it even outperforms LightGCN, a model that's specifically designed to find these complex, hidden connections between users and items.
So, what's the bottom line here? It's pretty straightforward. First, this diffusion approach completely shatters the old performance ceiling set by models like VAEs. Second, it somehow manages to learn even deeper signals than specialized models like GNNs. And finally, because its entire training is based on noise, it is naturally incredibly robust when it comes to handling the messy, noisy data of real-world user behavior.
But, and this is a big but, as exciting as all this is, DiffRec isn't quite ready to take over the world tomorrow. Like with a lot of groundbreaking tech, all this power comes with some very real, very practical trade-offs that we have to be realistic about.
The biggest hurdle, by a long shot, is speed. Traditional models are blazingly fast. Generating a recommendation for you is basically just one simple, quick math operation. But DiffRec, it has to do that slow, step-by-step denoising process for every single user, every single time you need a recommendation. In a world where websites need to respond in milliseconds, this iterative process is a massive, massive bottleneck.
And beyond just the speed problem, there are a few other headaches. For one, you're applying this smooth, continuous type of noise to data that's discrete, a simple yes or no click. It's a bit like trying to fit a square peg in a round hole. It works, but it's mathematically a little awkward. And finally, these models are just finicky. Getting all the little settings and schedules just right requires a ton of careful tuning, which makes them really tough to work with in a live production system.
But despite all those hurdles, let's not lose sight of the big picture here. DiffRec is a monumental achievement. It proves that framing recommendations as a denoising problem is a fundamentally new and powerful way to understand what people like, one that is just flat out more robust and more accurate than what we had before.
And that leaves us with one final, really tantalizing thought. Right now, there is an arms race happening across the entire AI world to make these diffusion models faster and more efficient. The question really isn't if they're going to get there, but when. And when the speed of this technology finally catches up to its incredible power, it might just fundamentally change how every single digital service we use understands what we want next.